So this is a sort of relaxing way of finishing. Talk about soot chemistry. I don't know an awful lot about soot chemistry, and I'm very grateful to my colleague Xiaoqing in Tsinghua, who has provided me with most of these slides, and also who's provided me with a research interest in one aspect of it. Okay. So why, interesting question, why does condensed matter form? Much of it is enthalpy driven. You can imagine that going from a gas to a solid is going to be going to have a negative entropy. The gas is much more random than the solid, and we'd expect to have a decrease in entropy from that process, and so it would need to be enthalpy driven. We'd need to be going down in energy as we form the solid. But soot is quite different, because what happens is you've got a molecule over here forming the solid carbon, but also eliminating quite a lot of hydrogen. And that process is endothermic, but it also has an increase in entropy because of the large number of molecules that you're producing. And so this shows what's going on. So this is taking propane and forming, first of all, acetylene, then forming benzene, naphthalene, pyrene, and eventually carbon over here, and eliminating hydrogen at each stage. And so although there is an increase in enthalpy, the important thing is that there is a significant increase in entropy. So this is minus T times S. So an important increase in entropy as we go along here. So soot formation is entropically driven. And here are some graphic pictures of soot, just in case you didn't know what it was. Now, just let's have another small atmospheric aside and talk about what's called radiative forcing, which is the change in the net radiation balance of the tropopause. Do you know what the tropopause is? The bottom bit of the atmosphere is called the troposphere. Above that, we have the stratosphere, and the boundary between the two is the tropopause, and that's a minimum in energy. When you go up into the stratosphere, the temperature starts increasing again, but as we go up in the troposphere, the temperature decreases. So the temperature is the minimum at the tropopause, and that's where the bulk of the absorption of radiation absorption of infrared radiation occurs at that low temperature regime. Radiation balance of the tropopause is caused by particular external factors in the absence of any climate feedback. So that's a bit complicated. So these forcing mechanisms can be caused by changes in the atmospheric constituents, such as greenhouse gases, aerosols, and changes in other components of the Earth, in particular, the way in which the Earth scatters radiation back out again to the atmosphere. So let's have a look at that. So we've got radiation coming in from the atmosphere. It hits, it's absorbed by the surface, and then infrared radiation goes back out again. And that infrared radiation can be absorbed at the tropopause by species such as CO2. Okay, so radiation comes in from the sun, it's absorbed by the Earth, infrared radiation gets emitted, and that infrared radiation can be trapped, and then some of it can come back again to the Earth, leading to heating. If we have white clouds, then what can happen is they can reflect the radiation or scatter the radiation back out again. So white clouds are good because they reflect and scatter that radiation. Black clouds are bad because they absorb it. So any soot in the clouds is a problem. And then finally, we can get the infrared radiation scattered back out again and absorbed by absorbing aerosols. Okay, has anybody ever seen this diagram here? No? This is produced by something called the Intergovernmental Panel on Climate Change. And it tells you what the radiative forcing is from different species. So this is a global average radiative forcing this is in 2005, from 1750. So 1750 is important because that was when the Industrial Revolution took place, or started to take place. And so we've been emitting CO2 in increasing amounts ever since then. And this is the amount, this gives us a measure of the amount by which CO2 is increasing the temperature of the Earth, and the amount by which it's done so since 1750. These are other greenhouse gases: methane, nitrous oxide, halocarbons. I mean, again, a substantial effect, about half that of CO2. And then this is ozone that's produced in the troposphere by the mechanisms we talked about recently. And that, again, is a greenhouse gas. Interestingly, water absorbs infrared radiation. But the point about water is it rapidly equilibrates with the surface of the Earth. But as we increase the temperature, then the amount of water vapor in the atmosphere is going to increase. And so that's what's called a positive feedback, and would lead to greater warming. Then these are aerosol effects. These are aerosol effects here. So this is scattering by aerosols in the atmosphere, by clouds and so on. And this is black carbon on snow. And that's not a good thing. So black carbon on snow leads to snow is great at scattering radiation back out again. If there's black carbon on it, then it absorbs the radiation and doesn't let it escape from the Earth. And so that's the total net effect. And so soot and climate, soot deposition is responsible for 95% of polar ice melting, which is a rather worrying statement. Dirty snow reduces the ice albedo. The albedo is the ability of the Earth to scatter the radiation. And if we've got black carbon on it, then it doesn't scatter the radiation as well. It absorbs it. Brown clouds cause regional warming. Have you heard of the Asian brown cloud? Especially over Southeast Asia and India. On occasions, there is a big brown cloud which comes mainly from wood burning and particles produced from wood burning. And then contrails are good because they give rise to scattering of the radiation back out from the Earth. This is emission. These are forest fires in Portugal, and the smoke from those forest fires. And you can see that over the surface of the Earth, this smoke is actually more reflective than the Earth itself. But when you get over here, over the clouds, then it's less reflected. So you decrease the reflection over cloud and decrease the planetary albedo, but you increase the reflection over the ocean in particular, because the albedo of the ocean is less than the albedo of this cloud that's going, the smoke that's going along. So local fires like that are very significant. Okay, now let's have a look at some soot chemistry. How is soot formed? So here's a flame, a sooting flame, and down the bottom we have the fuel plus the oxidizer, and that initially generates small radicals like methyl, vinyl, and in particular C3H3, the propargyl radical. And then these react together and generate small aromatics and these PAHs. PAH stands for polycyclic aromatic hydrocarbons. Then we get some form of polymerization or some form of making these growing molecules bigger and bigger. And so this is particle inception, the formation of the first particles, which have diameters of 1 to 2 nanometers. And then these particles grow by surface reaction and coagulation. So reactions occur on the surfaces and make them bigger, or particles coagulate together. And then eventually we're forming these much bigger clusters, sizes of 10 to 30 nanometers. And then we can also get oxidation, and we'll talk at the end a little bit about the oxidation of these particles. And so that's a picture of what's going on that's described over here. And the driving forces behind, so this is a whole set of, if you're interested in soot, then what Xiaoqing has tried to provide is, excuse me, a whole set of references. And this is the breakthroughs where Palmer and Cullis said in 1965, a major breakthrough in understanding carbon formation will have been achieved when it becomes possible, in at least one case, to account for the entire course of nucleation and growth of carbon on the basis of a fundamental knowledge of reaction rates and mechanisms. And that remains a major aim. But here is the soot volume fraction, experiments, and also theoretical descriptions of it. So some progress was being made in the 80s. And then these are references from the 90s and 2000s where there were substantial developments in terms of experimental measurements of soot formation, but also of modeling directly the soot formation in these complex systems. And so, again, this is a description of what that process occurs, going from small molecules, one-ring aromatics, increasing cyclization, eventually forming soot. So gas phase chemistry, pH chemistry, nucleation, and mass growth. So one of the key things is obviously going to be the formation of the first aromatic ring. These aromatic rings are really central to the overall process. So how does that first aromatic ring form? And we'll skip through quite a lot of mechanisms of how that might happen. So one of the first things is C3H3 and C3H3, these propargyl radicals, can react together to form a C6 compound which can cyclize. This is more C3 chemistry, where this is a diradical reacting with this propargyl radical, generating this species with a radical center there. C3H3 plus C3H5, and going down here, other radicals, a C4 radical reacting with acetylene, C4 reacting with acetylene in various ways, this one forming a radical center here. And then the formation of this species here, fulvene, which is a 5-membered ring, but with an additional carbon here that can lead eventually to benzene formation. So a whole host of possible mechanisms that we'll have a look at in a bit of detail. So formation of the first aromatic ring. And the understanding of this goes back quite some time to calculations carried out at Sandia by Jim Miller and Carl Melius. And so this is the propargyl radical, and the point about it is that there is an essentially allylic type of center here. This delocalization can occur where this radical center moves from here to here. So basically this electron density can come in here, the radical center can move essentially to there. So there are these two possible isomers. Well, they're not really isomers. They're because this occurs quite rapidly, going from one to the other. And so this is CH2, CCCH, this one, reacting together, and they come together to form this straight ring compound, which can react to form fulvene. Oh, not fulvene, sorry. This is a double bond here, a double bond here. And that can react to form fulvene, which can go over eventually to form benzene. And similar reactions here for this species, which can form this adduct, which can undergo a variety of reactions and eventually generate benzene. So these are calculations from 2003 from Miller and Klippenstein, and then from the Argon group of the formation of the first aromatic ring by these mechanisms. Some experimental data available for C3H3 plus C3H3 that can then be used to simulate the formation of the products. So these are big master equation calculations that were carried out to show these rates of reaction. And this is another mechanism whereby, sorry, excuse me, we take this species here, radical center, again, can be two forms of this species, the normal and the iso C4H5, and again, two reaction mechanisms that take place through these various wells, eventually generating cyclic species and benzene over here. So in this case, these reactions involve reaction of the C4 compound with acetylene. And so you're generating radical species going from this species, reacting with acetylene and forming species down here. So C5H5, this species reacting with CH3 along this sequence here to benzene, and here are the potential energy surfaces for it. And here's a reaction between fulvene, this species, and H, which eventually generates benzene plus H there. So obviously this has the same, this is also C6H6, this is C6H6, but this is a sequence of reactions following the addition of H to this position here and going down to form benzene. H plus fulvene, another look at it from Jasper and Hansen, and rate constants for the reaction. They're reaction rates that increase with temperature because there are activated processes involved here where the H has to add to the fulvene. Fulvene is quite a stable compound. And here we've got cyclohexane losing a hydrogen to form this radical, losing another hydrogen to form cyclohexene, and then losing another hydrogen to form this radical center, and so on. So a whole series of reactions where hydrogen is removed, for example, by reaction with OH, or more probably with H, and eventually generating benzene. And you can see the benzene formation depends upon the structure of the fuel. So this is a burner with different fuels looking at the formation of benzene as a function of distance from the burner. And some of these species react much more rapidly. Methyl cyclopentane reacts much more rapidly than the others. Now, this is an acetylene oxygen flame, and this is looking at the mass spectra as a function of distance from the flame. And you can see there's a wide range of species here, and a coalescence as we go up here, whereby they form these polycyclic aromatic hydrocarbons, these condensed ring systems. 2 rings, 3 rings, 4 rings, 5 rings. This is called coronine because it's rather like a crown. So this is from benzene plus O2, again the same sort of structure, coalescing and forming these polycyclic aromatic hydrocarbons. And this is one of the key mechanisms describing the growth of these polycyclic aromatic hydrocarbons. And this is called the Hacker mechanism, developed by Michael Frenklak's group, hydrogen abstraction, carbon addition. And so what happens is we take benzene and then you get abstraction. So H reacts with the benzene to generate H2 and this radical. And that radical then reacts with acetylene and forms this species here. We then remove another hydrogen atom here, again reaction with benzene, and then condensation to form this new species, new radical species, which is basically the naphtholenyl radical. And so you carry on adding another acetylene, losing another H, adding another acetylene, and forming this 3-membered ring, and so on throughout. So hydrogen atom is the driving, is actually driving the driving force behind chain branching and flame propagation. So there's a lot of hydrogen around in these flames, and acetylene is the most abundant hydrocarbon intermediate in fuel-rich conditions. And so that's the basis of this mechanism, why Frenklak proposed Hacker as a reasonable way forward. And these are the reactions that are involved in forming these PAHs. So down here we've got the small radical chemistry, which is the main flame chemistry. And then we begin to form the first aromatic ring. And this is one of the key reactions. You probably can't see it, but it's methylene reacting with acetylene and forming C3H3 plus H. And this is the singlet methylene, and this is triplet methylene. And you can see that both of those have got high sensitivity. This is C3H3 being removed by reaction with OH to form C2H3, and so that reduces the formation of the aromatic rings. And then what we've got down here are the basis of the Hacker mechanism leading to growth. So the A1, A2, A3 are these condensed ring compounds as we go through that. So this is Hai Wang and Michael Frenklak paper from 1997 looking at the sensitivity of this simulation of an acetylene oxygen argon flame using this Hacker mechanism. So this shows the energetics of the process in which we've got a hydrogen atom reacting to form H2 plus this species. So there's a decrease in delta G there, but an increase in delta G as we add the acetylene, and so on. And so while Hacker captures the thermodynamic requirements of pH formation, it is reversible, and it opens up competition to other pathways. So this is the changes in delta G are really quite small, and so that's why these reactions can be so relatively easily reversed. And so these are other ways of forming polycyclic aromatics. So these are 2 cyclopentadienyl radicals reacting together and forming this and eliminating a couple of H's. C5H5 plus C5H5 forming these linked compounds down here and reacting eventually to generate naphthalene over here. So these are alternatives. And there's something called the PAC mechanism, which is phenyl addition cyclization, which is an alternative route efficient for the growth of large pHs, while HACA is efficient for producing symmetrical pHs. So this is a route involving phenyl radicals. So phenyl radicals reacting together and losing an H, and eventually moving down and forming these large condensed compounds down here. Whereas this is HACA over here, leading to equivalent sorts of compounds. Okay, so those are the ways in which you form these large condensed ring compounds. We've still got to go along and form clusters of these in some way so that we can generate soot. So how does that happen? So path A here is, so these are various suggestions, the growth of two-dimensional pHs into curved fullerene-like compounds, structures that are the nucleus of spherical particles. Now, you've heard of fullerenes, which are these very large sort of football-like compounds. And so this is the mechanism for forming those. And is this how soot is formed? And the trouble is it's too slow to obtain the time scale, to explain the time scale of soot formation. What you could get is physical coalescence. So these big ring compounds simply come together. They're highly polarizable, and they can interact together and form clusters of compounds in that way. But the trouble is that's unstable at relatively high temperatures. And so what you need is chemical coalescence of pHs into cross-linked three-dimensional structures forming aromatic aliphatic linked structures. So the pHs have really got to react chemically together in order to form these soot particles. And then what happens is, so we start with these initial particles, and they can coagulate. In other words, two particles can come together here. They can, to form a single particle, they can agglomerate so that their identity is still there, but they're interacting with one another, and then they can coalesce and produce bigger and bigger species. The other issue is the growth of the soot surface. So how does, are there any ways in which reactions can take place at the soot surface and give rise to growth in that way? And so this is a suggestion. So here's a model compound simulating a soot surface. So this is basically a soot surface here with this benzene ring attached to it. And so what you've got to do in some way is to lose a hydrogen atom and generate a radical center here. And that's produced by reaction between this compound and the hydrogen atom, generating H2. And remember, H2 formation is a key process in soot formation, and this radical here. That radical can react with H and regenerate SiH, or it can react with acetylene. So acetylene can come on here and form a condensed ring at that point there. So what we've done here is by reacting with hydrogen, I mean, it's very much the HACA mechanism, reacting with hydrogen and then add it to generate a radical center, reacting with acetylene to generate a new ring on the surface. And that's going to depend upon, so this is equilibrated here, this reaction is reversible, and so the rate of reaction is going to depend upon the rate of this step here, multiplied by the concentration of Si, which is going to depend upon this equilibrated reaction over here. So this is a new process that we haven't discussed up until now. And that's something going on the surface whereby that surface is continuing to grow with time. And so here's a discussion of soot surface growth in adding acetylene and producing various species, these 5-membered rings here, and multiple 5-membered rings, and going over to these really quite complex structures over here. Okay, the other thing that can happen is the soot surface can be oxidized. So we can begin to lose carbon from the surface by an oxidative process. And so this is one example of the way in which it might happen. So we've got a radical center here, react with O2 and generate an oxyradical. And that oxyradical can eliminate, because of the presence of that oxyradical, we can eliminate CO, reducing the size of this ring here. And one of the interesting issues is the importance of these 5-membered rings, because these 5-membered rings can influence considerably the chemistry of what's going on around them. And they can migrate by these various processes. So here's this radical, and we can get an expansion of this ring, a contraction of that ring, and the radical center is there. So this is an isomerization process that's induced by the presence of this radical center and the presence of the delocalized system in the overall molecule. Or alternatively, what we can do is we can get O2 addition and CO2 removal so that this carbon compound here, carbon atom here, is removed and lost as CO2. And this is a way in which these 5-membered rings can move down from the surface into the bulk of the soot system. So embedded 5-membered rings where what's happening is we've got the radical center there, reacts with acetylene, and cyclizes across here so that we get a new C6 compound, C6 ring here, and that C5 ring moves further into the middle of the compound. And you can finish up with it moving really quite a long way down. So these are various oxyradicals being formed so there's the red oxyradical. So this is the soot surface, and this is a PAH. This is corannuline that is being used to simulate this soot surface and oxidizing that by the addition of an oxygen atom. So we're generating an oxyradical center there by reaction. And that can be influenced by the presence of these 5-membered rings here, and the closeness to the 5-membered ring is quite important. And so this is a reaction in which we've got this oxyradical here, and what it's doing is it's isomerizing by breaking this bond, breaking one of these bonds here, to produce this species here. We've got a carbon atom, carbon atom, carbon atom, oxygen atom, and it can eliminate CO and form this new compound over here. So that's a way in which carbon can be lost from these soot systems by reaction with CO. And so this is a whole series of calculated rate constants for this process, for this wide range of soot mimics, which are large PAHs, but with oxygen atoms sitting on them. And the 5-membered ring can have a significant influence on what's going on, and its influence diminishes as it moves further and further into the compound. Okay, now just let's it's quite hard, even when you're talking about soot, not to be tempted to talk about master equation calculations. So just let's have, in the final few minutes, just let's have a look at the complexity of the molecular systems that we're dealing with when we're looking at these soot mimics. So these are reactions of coraniline. Coraniline is a big compound. So there's coraniline. There's the oxyradical of coraniline. So coraniline has got these 6-membered rings around it, around a 5-membered ring in the middle. And we've got an oxygen atom there. And what we want to do is we want to have a look at the rate at which that eliminates CO and removes a carbon atom from the system. And this is an alternative reaction in which it eliminates water from the system. So there's no loss of carbon in this route, but this reaction, this is an isomerization reaction followed by a dissociation. This is an abstraction by H, and these two reactions are going to be in competition. And one of them is going to eliminate CO, and one of them is going to eliminate water. Now, we talked about this before, and we said that this molecule is really very big, so it's got a lot of vibrations, and so the densities of states are very high. And if you look at the Boltzmann distribution for this compound, then what you find is that it peaks at very high energies and extends from 200 kcal per mole to about 400 kcal per mole. I mean, those are incredibly high energies. And this isomerization process is about 47, somewhere over here. And the overall dissociation is only a barrier of 77. So this distribution lies completely above the dissociation limit. But of course, that energy is delocalized throughout the molecule. And in order for the dissociation to take place, you need some of it to be localized in this bond here. So you can break it, sorry, this bond up here, so you can break it and then eliminate the CO over here. So the energy has got to flow into a particular region of the molecule in order to allow this to happen. And so what we said is that you've got to isomerize from this species here to this species here before you can dissociate. And how does that happen? We said, well, the distribution lies well above this limit, and so these molecules are whizzing over there without any collisions occurring at all. And so these are the rate constants for the energy grains that we've got up here, going from F to F5. And then they can go back again as well. And so what's going to happen is that microcanonically, in other words, at a specific energy, F and F5 are going to equilibrate. And that's going to happen at another energy, and another energy, and another energy. And those are all going to occur before the molecule undergoes any collisions. Now, the extent to which that occurs depends to some extent upon pressure, but you've got to go to very, very high pressures before you begin to get collisional rate constants that are comparable with the isomerization rate constants. So how do we handle this? We said that if there's overlap between the energy relaxation eigenvalues and the chemically significant eigenvalues, then all bets are off for generating rate constants. And so what we do in this case is we say, okay, the equilibration is occurring very quickly, so let's allow these two to equilibrate, and let the reaction occur from an equilibrated system over here. So this shows the way in which everything is happening. This is at very high temperatures. F equilibrates with F5 very quickly, and this is a description of adding those two together. This is F prime, which is the equilibrated mixture of F and F5, and that's reacting away on longer timescales. So we can eliminate these short time effects by looking at the equilibrated mixture of F and F5. So we need a strategy then to determine the rate constant for going over this barrier. But what we've done is we've equilibrated these two. So we apply micro equilibrium for F and F5. What does that mean? It means that they're just equilibrating at specific energies. And what we can do is we can say the fraction that exists as F is equal to the fraction that exists as F5 divided by the densities of states of the two. So they're going to depend upon the relative densities of states. And we can express that as the fraction of the system that exists as F prime, the sum of F and F5, if we simply put the total densities of states in there. And then we want to look at the loss of F prime over that barrier to form the products. And so we have, excuse me, we have the sum of states for going over that barrier, but we use the densities of states for the whole system of F prime. So what we're saying is we've got these two equilibrated here. We're going over this barrier here. So we want the sum of states for going over this barrier, but the densities of states that apply is the density of states for these two species together. And so you put them together, and that's what you get. And the rate at which you go over the top depends upon pressure in a variety of ways. It's a fairly complicated story, which we don't have time to go into. Well, we do have time to go into, but I won't bore you with. And the decay of the reactant and the formation of the products are highly non-exponential at high temperatures. So dF4 by dt is equal to minus dF by dt, and we'll set that equal to K effective at a pressure and a temperature times the concentration of F prime, which is what we want. And how does this work out? Well, at 1500 K, what we could do is we could use the smallest eigenvalue. The smallest eigenvalue should be equal to the dissociation rate constant, provided there's no overlap between IEREs and CSEs. And at 1500 K, that works very well. There's no problem at 1500 K. The reaction isn't occurring too quickly for that overlap to occur. But at 2500 K, using that eigenvalue method gives you a rate constant which is too slow by several orders of magnitude. In addition, notice that the decay of F prime and the formation of the products is highly non-exponential. That's an exponential curve. And this one, it's much faster at short times, and it carries on for much longer times. The reaction goes from 90% to 10% over several decades of time. And so what you can do is you can try and fit it, and this is fitting it. This is basically reducing the sum of squares of the deviations. And so this is an exponential decay, which is fitted really to give the best fit to this curve. It underestimates the decay at short times, overestimates it at long times, but it's one of the best things we can do. If you're going to put this into a model, into a combustion model, into a mechanism, and then into a combustion model, you can't use time-dependent rate constants. You've got to use ordinary rate constants. And this, to describe this fully, you would need a time-dependent rate constant. It's not exponential. So all we can do is just approximate it by some phenomenological rate constant, but it's not going to reproduce exactly what's going on experimentally. And so this slide shows the effective rate constants at 0.1 atmospheres. And this is the eigenvalue method. This is the fitting method. And as you go up in temperature, you clearly, with the eigenvalue method, you don't do very well at all. You're doing much better with the fitting method, but there are problems. And where do we go from here? We've got in our models to use these approximate rate constants. We've got to fit them as best we can to the results that come out of the master equation model. But is that good enough? Because this reaction will be in competition with other reactions, and can we reflect that competition accurately with this only approximate rate constant? And that's still to be decided. That's work that still needs to be done. And so you need to watch this space. Your avid reading of the literature may, in a year or two's time, demonstrate how this can be done. Okay, any questions? Do you feel as shattered as I do?
Yep. A little bit like eating an elephant.
Okay. Well, thank you very much for staying till the end. I hope that you've got something out of the course. If any questions arise, you've got the notes. There will actually be there has been a video produced of all of this, brilliantly produced of all of this. I'm sure the last thing you want to do over the next several weeks is to see me again talking about all this stuff. But maybe in the future you may find that it would be useful to go and have a look at this video and try and understand some of the stuff that's going on with the notes and also with the references. If there is anything that you want to know additionally that comes up as you work so hard on this lecture course in the future, please don't hesitate to send me an email. I'm sure the email is, well, let me give you my email address. So it's m.j.pilling@leeds.ac.uk. So if there is anything that you want to know, then please don't hesitate to ask. And right on cue, here is Professor Law. Thanks very much.